Welcome to the afternoon session. We are delighted to have Pietro Berardi Gili from the University of Italian, Switzerland, to give us the talk towards the Truthmaker Semantics for modal logics. Thank you, Pietro.
Thank you very much for having me and for being here. So today I'm going to talk about how to extend the standard Truthmaker semantics for propositional logic to propositional modal logic. And in particular, the plan of the talk will be the following. So I will start with an informal introduction to the main ideas behind the semantics that I developed. Then we will move to our more formal setting, in which we actually introduce the precise, exact verification and exact falsification clauses for sentences of type box A and diamond A, so for languages containing modal operators. And then in the second part of the talk, I will focus on the logics supported by the framework that I develop here. And in particular, I will relate the logic of loose consequence in particular classes of models with systems of normal modal logic, and in particular with the standard possible words semantics for propositional modal logic. And then I will say something on how my framework compares to one of the most developed Truthmaker semantics for modal logic extant in the literature, the one developed by Kim. And lastly, if there's time, but I suspect there won't be time, I will say something on the two logics supported by the relation of exact entailment in the classes of models that I introduce. So let's start. Now, as you all know, Truthmaker semantics is a semantic framework that allows us to assign distinct contents to necessarily equivalent and even classically equivalent sentences. And this renders the framework particularly well suited to handle paradoxes that arise in the context of standard possible word semantics when we try to give semantics for sentences involving a modal operator. And in particular, I have in mind paradoxes that have to do with epistemic modalities. So, for example, the paradoxes of logical omniscience and the paradoxes of standard deontic logic, if we are interested in languages that contain deontic modal operator. So for this reason, I think it is particularly interesting to try to develop Truthmaker semantics for modal logic. And this has already been done in the literature, but most of the accounts developed do not support an iteration of modal operators. So they provide semantic analysis only of modal sentences which contain just one modal operator, but not iterated modal operators. There are some exceptions, such as, for example, the account by Kim that I will examine in this talk. But indeed, the objective here is to try to develop a semantics that is suitable for the full language of propositional modal logic. And to do so, I adopt an idea that's already been introduced in the literature that involves adding to the standard state spaces of Truthmaker semantics two relations that behave as modal counterparts of exact verification and exact falsifications. In particular, I call these two relations exact allowance and exact exclusion. I take allowance and exclusion to be two relations between states and unilateral propositions, so sets of states. And intuitively, let's adopt for our examples a metaphysical interpretation of exclusion and allowance. We say that a state S excludes a unilateral proposition P, just in case S sees P as impossible. We are adopting a metaphysical interpretation. And S is also wholly relevant to P's impossibility. And similarly for allowance, we say that a state S allows a proposition P, just in case S sees P as possible and S is wholly relevant to P's possibility. Now, of course, as you can see from the slides, also other interpretations are available. So, for example, we could adopt a deontic interpretation of exclusion and allowance or an epistemic one. But here we'll focus on the metaphysical case since it's simpler from the point of view of the examples. Now, it should also be clear the sense in which exclusion and allowance are analogous to exact verification and falsification. Because, as you know, a state exactly verifies a given sentence just in case it makes it true and is wholly relevant to its truth. And this here, what we have is analogous. For example, a state will allow a certain proposition just in case it makes it possible in the relevant sense and is wholly relevant to its possibility. So this is the analogy between, for example, allowance and verification and exclusion and falsification that I have in mind. Now, in order to better understand what it is for a state to see a proposition as possible or impossible, we can think of states as in some way representing laws and adopt a metaphysical interpretation of exclusion and allowance. So we can think of state as representing laws since we can coherently think of laws as being the source of the modal status of propositions. So in this sense, it will make sense to say that a state sees a certain proposition as impossible or possible. In particular, I have in mind examples such as the following. So we may let S, for example, be the state of the law of conservation of energy holding. So S is the state that reality is in, just in case the law of conservation of energy holds. Similarly, we may let T be the state of all known physical laws holding. And we may let U be the state of Socrates being wise, for example. So a state which is non-modal in nature, which does not correspond to any law. Now, consider the proposition P, the proposition that two pool balls stop upon impact. Clearly, S, T, and the fusion of S and U all see P as impossible in some sense, because all these states entail that a certain law holds, and this law excludes the truth of P, since the truth of P is something that is not allowed by the law in any possible counterfactual circumstance which is consistent with the law itself. But, however, only S will exactly exclude P, because S among these three states, S, T, and the fusion of S and U, is the only state that does not include material that is irrelevant to the question of whether P, the proposition we have here in the example, is possible or impossible. Similarly, for allowance, since, well, in this example we are considering physical laws, since physical laws do not only allow us to exclude certain scenarios, but also allow us to recognize certain scenarios as genuine physical possibilities, it will make sense to say that a state of this kind, which represents a law, exactly excludes a particular proposition. So this is just to get a clear idea of what I mean by exact exclusion and exact allowance. Now, with these two relations in place, we can give very simple and intuitive exact verification and falsification clauses for sentences of type box A and diamond A. So, for example, we can say that S exactly verifies box A if S exactly excludes A is being false. So, if S exactly excludes not A. Similarly, S will exactly falsify box A if S exactly allows the falsity of A. So, if S exactly allows not A. And we adopt the dual clauses for diamond A. So this is the main idea from an intuitive point of view. Now we will see how these ideas can be turned into a formal semantics for the language of propositional modal logic. And as I said, we will focus then on the notions of loose consequence and exact consequence, and on the logics supported by these notions. Now, here I have a very basic introduction to the main notions that we use when we develop a Truthmaker semantics for propositional logic without modal operators. So we just have the notion of state space. I assume that state spaces are closed under arbitrary fusions. And I use the standard notation for the fusion of states and the fusion of propositions. So the fusion of two propositions, P and Q, will just be the set of states that are the fusion of some state in P and some state in Q. Also, just to be clear, throughout this talk, I will use proposition as synonymous with unilateral proposition. So we will not deal with bilateral propositions. Then we also have the notion of P space, which is just what we obtain when we add to a state space a distinguished set of possible states, which is, of course, required to be downward closed under parted and non-empty. Given a P space, it is well known that we can introduce these notions, in particular compatibility and incompatibility. So we say that a state is compatible with another, just in case their fusion is possible, and incompatible otherwise. And we say that a state is compatible with a proposition, just in case it is compatible with some element of the proposition. A proposition is, again, just a set of states, and incompatible otherwise. Lastly, we say that S is a word state or a possible word, just in case S is possible, and all states that are compossible with S, so that are compatible with S, are part of S. So a word state is simply a possible state that includes whatever is compatible with it. We can get models from state spaces and P spaces simply by adding two functions which associate to each propositional letter a set of exact verifiers and a set of exact falsifiers. And this is, again, all standard. Now, the clauses I will adopt throughout this talk are the non-inclusive clauses. So these are just the standard clauses that you find in Truthmaker semantics. They are non-inclusive since a verifier, an exact verifier, for example, of a conjunction. No, sorry, the other way around. Well, yes, because, for example, if you consider an exact verifier of a disjunction, then an exact verifier of a sorry, I'm getting confused. But again, simply this is to say I'm using the non-inclusive clauses rather than the inclusive ones. So the semantics we will get out at the end is one in which, for example, a sentence of type A and a sentence of type A and A, so a self-conjunction, will not necessarily be semantically equivalent. So self-conjunctions may express distinct propositions than the individual conjuncts. I also use an implication connective, and this just stands for material implication. So the clauses I adopt guarantee that the exact verifiers and falsifiers of a sentence of type A plus B are just the same of the disjunction not A or B. And it is all straightforward. I use the standard notation for the set of verifiers and falsifiers of a given sentence in a model, and the standard definitions of the notion of inexact verification and inexact falsification. Now, this is the new part. So how we actually extend the semantics for propositional logic to one for propositional modal logic. And as I've already said, we do this by adding two primitive relations to our models, which are exact exclusion and exact allowance. And we take these to be relations between states and propositions. So both triangle E, exact exclusion, and triangle A, exact allowance, are subset of the Cartesian product of the set of states and the power set of the set of states. And by adding these two relations, we obtain modal spaces and also MP spaces, depending on whether we add them to a state space or we add them to a P space, which also has a distinguished set of possibilities. Now, with these two new relations in place, we can define several interesting notions. So, for example, we can associate each state to the set of propositions that it exactly excludes or exactly allows. And this is what E and A represent. So our functions that associate each state to the set. And also we have EI of S and AI of S, which I call S is fear of exclusion and S is fear of allowance. And these are functions that associate each state to the set of propositions that it exactly or inexactly excludes or allows, respectively, where inexact exclusion and allowance is defined simply as having a part that exactly excludes or having a part that exactly allows. So this is analogous to what we do for exact verification, inexact verification and inexact falsification. Similarly, we can define two operations on propositions, E and A, sorry. And E of P will be just the set of states that exactly exclude P, and A of P will be the set of states that exactly allow P. And we will see shortly that these two operations on proposition correspond semantically to the modal operators not possible and possible applied to sentences. Again, we obtain models from state spaces and MP spaces by adding the usual evaluation functions. So this is not new. And again, we adopt the clauses that we have seen also in the introduction, according to which S exactly verifies box A if and only if S exactly excludes the negative proposition expressed by A, so the set of falsifiers of A. And we have the dual clause for exact classification with allowance in place of exclusion. And for sentences of type diamond A, we have the set of verifiers of the sentence A instead of the set of falsifiers. We can also represent these clauses algebraically via the operations on propositions E and A that I introduced before. Now, lastly, we define, well, as is well known, Truthmaker Semantics supports several notions of consequence. Three notions of consequence that I define here, but these are not the only ones, are exact consequence, inexact consequence, and loose consequence. We shall focus just on the first and last ones. So we say that A is an exact consequence of gamma, where gamma is a set of premises in a class of models. Just in case for all models in the class and all states in those models, if the state exactly verifies all premises B in the set of premises gamma, then the state also exactly verifies the conclusion A. So exact consequence is just preservation of exact verifiers. For loose consequence, I use a slightly different definition than the one you find in the literature, but it's actually equivalent to the standard one, which says that A is a loose consequence of gamma in a class of MP spaces, in this case, just in case for all possible states in all models in that class, whenever the possible state exactly verifies all sentences in gamma, the possible state does not inexactly falsify the conclusion. So here we have inexact verification implies not inexact falsification for loose consequence. Now, I now move to the logic of loose consequence, the modal logic supported by the relations of loose consequence. And we will see actually that well, that loose consequence allows us to interpret Kripke semantics in the sense that given a class of Kripke frames, logical consequence in that class of Kripke frames will coincide with loose consequence in a particular class of MP spaces. Now, we know that, let's start from the beginning. So we know that if we are working with propositional logic, then classical logic is sound and complete with respect to the class of models, of Truthmaker models that satisfy these two constraints, exclusivity and exhaustivity. Exclusivity tells us that no exact verifier of a propositional letter is compatible with some exact falsifier of the same letter. And exhaustivity tells us that all possible states are compatible with either an exact verifier of a given propositional letter or an exact falsifier of that same propositional letter. And this is well known. Now, moving on to modal logics, if we want to recover classical logic in a setting in which the underlying language is that of modal propositional logic rather than that of propositional logic simply, we also have to add two constraints which, in a sense, are modal counterparts of exclusivity and exhaustivity. And in particular, here we have modal exclusivity, which tells us that for all states, if a state excludes a certain proposition, then that state is incompatible with all states that allow a proposition. So if two states, one excludes a proposition and the other allows it, then the two are incompatible. This is what modal exclusivity says. For modal exhaustivity, here we have instead a modal analog of exhaustivity. And this tells us that given any possible state and given any proposition, the possible state must be compatible with either a state that exactly excludes the proposition or with a state that exactly allows the proposition. Once we have these two constraints in place, we can actually show again that classical logic is both sound and complete with respect to loose consequence in the class of classical models, that is, models that satisfy the two constraints we have seen before, so exclusivity and exhaustivity, and which are also based on MP spaces which satisfy the modal analogs of exclusivity and exhaustivity. If instead we want to recover systems of normal modal logic, we have to impose a further constraint. To state this constraint, I first introduce a definition. So we say that a state S complies with a state T, just in case for all propositions which are in the sphere of exclusion of T, S is incompatible with those propositions. So for S to comply with T is for S to be incompatible with everything that is excluded by T. So we may think of a state that complies with T as a state that conforms to the modal opinions of T. Now, with this definition in place, we can state the constraint that will allow us to recover the modal logic K, and which is normality. And normality tells us that for all possible states and for all propositions which are in the sphere of allowance of those possible states, there is a state that complies with the original possible state and is compatible with the proposition. So the idea behind the normality constraint is that if P is a proposition in S's sphere of allowance, then P should be compatible with some state that is not compossible with what is taken to be impossible by S. So the idea is just that if we start with a possible state and we look at its modal opinions, there should be a possible state that complies with those modal opinions. And we let N here be the class of MP spaces that satisfy normality, as well as the previous two constraints, that is modal exclusivity and modal exhaustivity. And it is easy to show, it's fairly easy to show that N, K, the logic K, is sound with respect to loose consequence in N. So the constraints we have introduced so far allow us to recover the K axiom and the rule of necessitation. To show that K is also complete with respect to said class, we actually prove something stronger. That is, we prove that, as I anticipated, the semantics we have here interprets Kripke semantics, in the sense that for all classes of Kripke frames, there is a corresponding class of MP spaces such that A is a loose consequence of gamma in the class of MP spaces, if and only if A is a logical consequence of gamma in the class of Kripke frames. To obtain this result, we construct a function that associates to each Kripke frame a corresponding MP space. So this works as follows. So we start with a Kripke frame WR, where W is a set of words and R is just a relation of accessibility. And we define the corresponding MP space of our starting Kripke frame as the unique MP space that satisfies these constraints. So first, the set of states is identical to the power set of W. So it's just a set of words. Then we take the part of the relation between states to be just supersetted, so that, for example, the state that the singleton of W, for example, will have as a part the set that contains W and V, for instance. Then we identify the set of possible states with simply the set of non-empty states. And then we use these definitions of exclusion and allowance, which, well, maybe are not intuitive at a first glance, but they just correspond to the idea that for a state S to exclude a proposition is just for all the words in that state to have a sphere of accessibility in the sense of R that does not intersect that of any word in some of any state in P. And what we have for allowance is just the dual of this clause. And the main idea behind this construction is simply that we identify states with the set of words at which they obtain. So this idea allows us to construct a correspondence between Kripke frames and sets, and MP spaces. Now, with this construction in place, we can actually establish some results, which I will not go through. But what we get out at the end is that, indeed, if you start with a class of Kripke frames, CF, for example, and you take the image of that class under I, the function we have just defined, then logical consequence in CF will coincide with loose consequence in the image of CF under the function I. And so this, together with the fact that the corresponding MP spaces are always normal, so always satisfy normality and all the other constraints we introduced, immediately gets us the completeness result. This can be generalized to stronger systems of modal logic, and in particular with the interpretation result that we have in place, we can show that a given normal modal logic L is sound and complete with respect to a class of normal MP spaces, C, by simply showing that L is sound in C and that the canonical Kripke frame FL for L is such that its corresponding mod frame IFL is in C. So, yeah. So this is a strategy that works for all systems of modal logic. In particular, here I have applied it to those systems that can be obtained by extending K to some of the axioms that you find here. So to at least one or more of D, T, B, 4, and 5. And we can associate each of these axioms to a corresponding condition on MP spaces. And it is similar to what we do in the context of Kripke semantics, where we associate axioms in modal logic to conditions on R, usually. Okay. How am I doing on time? Okay, thank you. So, okay, turns out that I won't have the time to go through the logic of exact entailment that I would have liked to discuss. So if you're interested in that, you can ask it during the Q&A. So I will just conclude by comparing the account I have developed here with the one by Kim. So there are two main differences between the Truthmaker semantics that I have presented and the one and Kim's approach. And the first difference is that Kim works with two primitive state-to-state exact exclusion and allowance relations, while we have worked so far with two primitive states-to-propositions relations. So this is a difference between two approaches that we can take when we extend Truthmaker semantics to modal logic. We can either work with the state-to-state relation or with a state-to-proposition relation. And second, the second difference is that Kim does not treat the notion of a possible state as primitive. Rather, it defines the set of possible states in terms of exclusion and allowance. Let us examine both differences in more detail. Now, for the first difference, in order to be clear about what exactly does this difference amount to, I introduce rigorously the notion of a Kim space, which is Kim's counterpart of an MP space, the one we have seen before. And here, as you see, we have S and partude as obvious, so we have a state space. But the state space is augmented not with two states to propositions relations, but with two states to states relations. So these black triangles that you have on the slides are used to represent these two relations. And in this case, they are subsets of the Cartesian product of S with itself. Given the state-to-state exact exclusion and allowance relations, our states to propositions relations can be defined, turn out to be definable in terms of the state-to-state ones. And in particular, we can adopt these definitions. So we take S to exactly exclude a proposition P, just in case X is the fusion, just in case S is the fusion of some states, such that each of them exactly excludes some state in P, and they all together exclude all states in P. And this can be made precise via the definition we have here. And for allowance, the idea is even simpler because we take S to exactly allow a proposition P, simply if there is a state T in P such that S exactly allows T. Now, how do the two approaches compare? Well, one thing that we may want to say is that the relation between the two approaches is somewhat analogous to the relation that we have between Kripke semantics and neighborhood semantics in the context of standard possible word semantics. So why this is? Well, because the state-to-state approach may in a sense offer greater explanatory power than the states-to-proposition approach, in the sense that certain conditions that one may want to impose on the states-to-propositions relations may turn out to simply be derivable in terms of the definitions of the states-to-proposition relations in terms of the states-to-states counterparts. Nevertheless, the states-to-proposition approach is more general, in the sense that there are several states to propositions relations which are not the corresponding states to propositions relations of any states to states relations. So if we work with the states to proposition approach, we can allow for a wider range of exclusion and allowance patterns. And finally, under the states to proposition approach, we can obtain an interpretation result for neighborhood semantics, which is analogous to the one I have presented before for Kripke semantics. And it is not clear whether this can also be done within the state-to-state framework. With regards to the second difference between my semantics and Kim's, this difference, in a sense, appeals to how the notion of possible states is introduced. As you have seen, I have taken the notion of possible state as primitive because we take S diamond, the set of possible states, to be a primitive component of an MP space and an MP model. While in the context of Kim's framework, the notion of possible state is defined and is introduced in particular to a series of definitions. First, we say that S is modally consistent if and only if there is no proposition that is both exactly excluded and exactly allowed by S. Then we say that S is a modal boundary just in case S is modally consistent and has no modally consistent extension. And finally, Kim defines the notion of possible state by saying that S is possible just in case S is part of some modal boundary. But now this definition causes a bit of trouble because given these definitions, it is easy to show that all modal boundaries are word states in the sense that we have introduced at the start of the talk. So a word state, recall, is a state that is possible and that includes all possible states that it is compatible with. And thus, Kim's framework cannot accommodate for MP spaces which are not word spaces. So cannot accommodate for MP spaces in which every possible state is properly extended by some possible state. So in the context of Kim's semantics, every possible state is always extended by some possible word. But as it turns out, there is no need to make this assumption. So from the point of view of the semantics, everything works fine, even if we do not assume that every possible state is extended by some word, because in our framework, we do not need to make any such assumption. And indeed, for example, it turns out that there is a normal mod space, normal in the sense that it satisfies normality, such that S5 is sound with respect to consequence in that mod space. Mod space, sorry, is just synonymous with MP space. And such that in this particular MP space, every possible state is properly extended by some possible state. So there are no upper bounds, there are no words in this sense. And for example, we can construct such an MP space simply by considering the set of finite ordinals and by letting the set of finite ordinals represent the set of possible states. And so here we will have no words because each finite ordinal has a successor. And the least upper bound of all the finite ordinals will not be a possible state, so it will not be a possible word. Okay. Thus, in conclusion, the semantics we have developed allows for MP spaces which are not word spaces. And we can show, since recall that S5 was sound in the MP spaces I showed before, that even very strong systems of normal modal logic, such as, for example, S5, indeed, are sound in some MP spaces in which every possibility is properly extended by some possibility. And this shows that even those who believe that modal reality is, in a sense, essentially open and incompletable, in the sense that every possibility is properly extended by some possibility, may be perfectly entitled to reason with strong modal logics, provided that they assume the constraints we have here. So I conclude that this second difference renders the semantics I presented, in a sense, preferable to Kim's semantics, because it doesn't build in the assumption of possible words, so that every possibility is extended by a possible word. And so that's it. Thank you.